We're continuing with section 3.2, and this time derivative and motion. A particle moves along a straight line. The function s of t represents its distance from a fixed point at a time t. Now, let's talk about what it means to take the derivative of s of t. The velocity of the object at time t is v of t equal to s prime of t, which is a derivative of s with respect to t, ds over dt. The acceleration at time t is a of t. A of t is the second derivative, s double prime of t, equal to v prime of t. See, what is happening is that if you take a derivative of s prime one more time, you end up with s double prime. And that is exactly taking derivative of v one time. And so it's the second derivative of s with respect to t. And that is d2s dt2. And that equals to dv dt, which is the derivative of v with respect to t. So, so far, v is the first derivative of s. A is the first derivative of v and second derivative of s. And what about the third derivative? The jerk at time t is j of t equal to j, and j of t is equal to s triple prime of t equal to v double prime of t equal to a prime of t. So basically, j of t is the instantaneous rate of change of acceleration. The other notations for that is d3 d3s dt3 d2v dt2 and da dt. And so it's the derivative of s with respect to t, the third derivative of s with respect to t here, and then the second derivative of v with respect to t, and then first derivative of a with respect to t. And this is the jerk is also responsible for you feeling nauseous on the roller coasters, because not only the acceleration is high, acceleration is changing basically. Now, units for these are, for s of t is the units of distance, for v of t units of distance over time, then a of t units of distance over time squared, j of t distance over time cubed. So let's talk about derivative rules. It doesn't make sense that every time we want to find a derivative, we have to use the limit definition. Is there any way that we can basically find the derivative and it's faster? And so yes, there is. You can use the derivative of constants. Although knowing the limit definition improves your understanding of what derivative really is, and in special cases you can figure out how to find a derivative just with the derivative rules. This is not possible. So first thing is derivative of constant. What is derivative of, let's say c is a constant? How do you take the derivative of c with respect to x? According to the limit definition, this is equal to limit of h goes to 0 as approaches 0 of f at x plus h minus f of x divided by h. What is f in here? F is c. F of x being c. So this is basically limit as h approaches 0 of c minus c over h. That is limit as h approaches 0 of 0 over h. And so if you imagine the 0 over h is 0 everywhere except for h, and since we're finding the limit it doesn't matter what value it takes at h. And so, because it doesn't exist. And so what happens is that this limit is going to be 0. Next, let's introduce a constant multiple rule. That's if you're taking derivative with respect of c f of x with respect to x, c is a constant multiple, then it's going to be c times derivative of f, basically. And so this is another way. So it's going to be c times derivative of f with respect to x. How do I explain this? Using the limit definition. Again, I'm going to go h goes to 0, and what I have is basically c f of x plus h minus c f of x over h as h goes to 0, and in here I can factor a c, and it comes out of the limit. I end up with this. According to the limit law, I can do this, and then this is basically derivative of f. So it's c times derivative of f. And so this is the constant multiple. So the next rule to notice is sum and difference rules. And so as constant multiple rule for derivatives is a consequence of constant multiple law for limits, and this sum and difference rule for rules for derivative are consequences of sum and difference sum law for limits. And so what does it say? I'm not going to show it like I did for those two, but this one is saying that derivative with respect to x of the sum or difference function f of x plus minus g of x is equal to the derivative with respect to x of f of x plus minus derivative with respect to x of g of x. And again, you can use the limit laws to prove that. The power rule, derivative with respect to x of x to power n is exponent, which is n, x to power 1 less, n minus 1. And then differentiating polynomial is now very simple. Why is that? Because first I can use the sum and difference rule, and then after I break each term down, then I can use the constant multiple rule, then I can use the power rule and differentiate. So first we write derivative of each term, and there's a plus and minus between them, right? And then at this point, when you're, for example, writing derivative of negative 12 x to the power 4, I know by the constant multiple rule 12 can come out of the derivative right there. And then at this point, what I need to do is to do a power rule here, another power rule here, another power rule here, another power rule here, and then this is the derivative of constant, which is 0. And so that's what we do. So power rule, the first power rule gives you 7x to the power 6. The second power rule gives you 3 times x to the power 3, 4 times x to the power 3, I'm sorry. But that 4 multiplies by 12, so it becomes 48 x to the power 3. Then here x squared becomes 2x, and derivative of x becomes negative 1, and derivative of negative 3 is 0. So the rate of change, instantaneous rate of change for constant, is 0, and that makes sense, right? Because